Question 9. You've got a 5 gram sample of potassium chloride adding to 50 grams of water that's initially at 20 degrees C. The mixture is stirred and the potassium chloride dissolved, the temperature decreased. Describe the steps you would take to determine the accurate minimum temperature not influenced by the surroundings. So normally the kind of experiment you're doing is to work out a temperature change, and then you can use delta H equals minus MC delta T. So if you're trying to find a temperature change, normally you carry out this procedure. You'd add the water, the 50 grams of water, to an insulated beaker with a lid. Start a stop clock, take the temperature of the water for 3 minutes. Don't do anything at time 4, or don't take any readings at time 4 rather. At time 4 you're going to be adding the potassium chloride to the water and stirring. You don't take the temperature at time 4 minutes because that's when you're adding the potassium chloride and stirring. Continue to take the temperature each minute for at least 5 further minutes. Plot a graph of temperature versus time. Extrapolate, which means extend the lines, the first line forward to 4 minutes and the second line backwards to 4 minutes, and then measure the two temperatures and subtract the two temperatures to find the temperature change. That's the normal standard experiment, and then using that temperature change delta T, you can use delta H equals minus MC delta T. However, the question is slightly different. It's told you the initial temperature is 20 degrees C, so you don't need to do the first step where you're measuring the temperature for the first 4 minutes or 3 minutes and then adding it. You can ignore that step because you know the initial temperature is 20 degrees C. You're not actually asked to work out either the temperature change. All you're asked is for the final temperature. So you can amend this so that it looks like this. You add the water to the insulated beaker with a lid, and you start the stop clock, add the potassium chloride and stir. So you don't need to work out the initial temperature. Take the temperature each minute for 5 minutes. Plot a graph of temperature versus time, and then extrapolate your line back to see where it hits the time when you added the potassium chloride. And then just take that time. So you're not even asked to work out the temperature change, so work out the new temperature, take away 20 degrees C. All you're asked to do is extrapolate the line back and calculate the temperature when you added the potassium chloride. Question 9.2. The temperature of the water decreases to 14.6. Calculate a value in kilojoules per mole for the enthalpy solution of potassium chloride. Okay, so Q is MC delta T, or delta H equals minus MC delta T. So delta H has got the minus value in because delta H has a minus value, expecting it to be exothermic. Q doesn't have that value, and you have to put the plus or the minus in at the end, depending on whether it's exothermic or endothermic. M is the mass of the liquid that's used, 50 grams. Delta H equals minus MC delta T, so you've got minus 50 is the mass of the liquid. C is the specific heat capacity, which you're already given, 4.18 joules per Kelvin per gram. Multiplied by the temperature change. Well, the temperature change has gone down from 20 to 14.6, so it's gone down by minus 5.4. The minus means the temperature has gone down, and when you multiply all those out, you end up with 1128.6 joules. You know it's in joules because the specific heat capacity has got joules as one of its units. You can convert that into kilojoules, and I'm going to do that at the end because it asks for it in kilojoules in a minute, but I'm going to do that at the end. Now I've got to work it out for 1 mole. Well, the MR of potassium chloride, potassium's 39 and chloride's 35.5, so it comes out as 74.6 moles of potassium chloride is the mass divided by the MR. The mass that you've got is 5 grams. Divided by 74.6, I've got 0.0670 moles. I've got a lot less than 1 mole. So this is the amount of energy that's taken in. So that's the energy that's gone down because it's an endothermic reaction. It goes down, so that's a positive value. So that's the amount of energy that it's gone down by when you've added 0.067 moles. Okay. So now I've got to scale this to a value, for imagining that you had 1 mole. So what I do is I do 1 divided by 0.670 gives my scaling factor to imagine what the enthalpy change would be for 1 mole, and I multiply by 1128.6. So it's 1128.6 multiplied by 1 divided by 0.0670, and that turns out to be 16,839 joules per mole. So I've worked it out per mole now, so by scaling this value up. I now need to put it into kilojoules, so going from joules into a larger unit value of kilojoules, I divide by 1,000, so that turns out to be 16.839, and I've got to get it to three significant figures rather, because everything else is to 3 significant figures, so it turns out to be 16.8 kilojoules per mole. The enthalpy solution of calcium chloride is minus 82.9 kilojoules per mole. The enthalpies of hydration of calcium ions and chloride ions are minus 1650 and minus 364 kilojoules per mole respectively. Use these values to calculate the value of the lattice enthalpy of dissociation of calcium chloride. So what actually happens? A lattice enthalpy is the energy required to break a lattice. And so when it dissolves, what you actually do is the enthalpy of solution is the value required to break the lattice, which is the lattice enthalpy, but you get some energy back, so you're going to need some energy to break the lattice, but you get some energy back when these particles hydrate, in other words, bond to the water, a process called hydration. It tells you these values here. So my enthalpy of solution is the process of dissolving the solid, so the enthalpy of solution is minus 82.9, and that equals the lattice enthalpy, the energy required to break up the lattice when it dissolves, plus the energy that you get back when it starts to bond to the water. So minus 82.9 is the lattice enthalpy added to the values of that hydration when they bond to the water. Now in calcium chloride is CaCl2. You know that because calcium's in group 2 and forms Ca2 plus ions. Chloride is in group 7, forms Cl minus ions. So calcium chloride is Ca2 plus Cl minus, but you need 2 Cl minuses to balance out the Ca2 pluses, so it's CaCl2. So I've got 2 lots of chloride ions, 1 lot of calcium ions. So I've got the enthalpy of solution minus 82.9 is the lattice enthalpy added to minus 1650, which is the energy that I get back, the energy that's released when calcium ions bond to the water when they get hydrated, and 2 lots of minus 3640 because there's 2 moles of chloride ions in there. That ends up as minus 82.9 is the lattice enthalpy plus minus 3300. Take that across to the other side. 3300 minus 82.9 is 2295, and it's in kilojoules per mole. Explain why your answer to 9.3 is different from the lattice enthalpy of magnesium chloride. Well, you've got to look at the size of the ions, or the difference between calcium and magnesium. Magnesium's a much smaller ion. It's further up group 2, so it's got 1 less energy level, 1 less electron shell. So it's a smaller ion, and a smaller ion will attract the calcium ion more strongly because the particles, the ions, can get closer together and form a stronger ionic bond. Table 5 shows some observations from some test tube reactions of aqueous solutions of compounds Q, R and S with different aqueous reagents. And the colours of the compounds formed and whether the solids, precipitates, etc. are shown. So the observations, it doesn't tell you the initial colours of these. So let's have a little look. Barium chloride. Barium chloride is used to test for sulfates because it makes barium sulfate used in barium meals. So this is some kind of sulfate here. These two are not sulfates. Silver nitrate with nitric acid. That's used to test for chlorides, bromides and iodides. Silver chloride is a white precipitate, so R is something chloride. And a cream precipitate is a bromide, so Q is something bromide. So we've got something sulfate, something chloride and something bromide. A bromide, a chloride and a sulfate. Now let's have a look what happens with sodium hydroxide. I get a brown precipitate here, something hydroxide that's brown. So something that's brown, a coloured substance, is usually a transition metal. So I'm looking for a transition metal. A transition metal, a coloured solution that's brown. I know that iron hydroxide, iron 3 hydroxide, is a brown precipitate. So this is iron 3 sulfate. I'm just going to check here. A brown precipitate, bubbles of gas. Yes, iron 3, something that's charged 3 plus, is acidic. I'm going to give bubbles of gas with a carbonate, so that's correct. And a yellow solution, yeah, it's going to form FeCl4 minus as a transition metal complex ion. But I know it's a sulfate because it's given a white precipitate with barium chloride, which is used to test for sulfates. And I know a brown precipitate with sodium hydroxide will be FeH2O3OH3. And we'll see that in the second half of the question when we're asked to do equations, but it's iron 3 sulfate. Let's have a look what Q and R could be. We've got a white precipitate here, something hydroxide, so something forming a hydroxide, maybe something like magnesium. Magnesium carbonate would be a white precipitate as well. I think this is magnesium. I know that it's going to be something in group 2, because it's white. If it were a transition metal, it would be a coloured solution, and if it were in group 1, it's not going to form precipitate. So sodium compounds and potassium compounds in group 1 don't form precipitates. So I'm probably looking at something like magnesium bromide here. What's happening here? A white precipitate that dissolves in excess sodium hydroxide. You're looking at something like aluminium. Aluminium isn't a transition metal, and it also is, aluminium is Al3 plus because it's in group 3, and that will be acidic and form white bubbles of carbon dioxide with a carbonate. So I think a white precipitate of aluminium hydroxide that dissolves in excess sodium hydroxide is aluminium. So I've got, let's just recap, I've got magnesium bromide, I've got aluminium chloride, and I've got iron 3 sulfate. Write the ion equations for each of the positive observations with S. So that's iron 3 sulfate. So I'm looking for, first of all, barium sulfate to make barium sulfate. Now barium is in group 2, so it's going to be Ba2 plus. Sulfate is SO4 2 minus to form BaSO4. I know it's BaSO4 because Ba is 2 plus, SO4 is 2 minus, and therefore it's just BaSO4. So that's my first equation. Ba2 plus plus SO4 2 minus forming BaSO4 as an ionic equation. Next one with no change observed here, so we're on to the brown precipitate. So we're on about Fe3 plus and 3OH minus ions, or FeH2O6 3 plus because it forms a complex ion. The 3OH minus ions replacing the 3 ligands. I know that there's 3 in there, and I know that it's got no charge because that's a solid. It says it's a precipitate, and it'll make 3 waters released from the complex ions, releasing 3 of the H2Os. Next one is precipitate bubbles of a gas. So FeH2O6 3 plus is my complex iron 3 ion. Carbonate ions are CO3 2 minus. If you weren't sure of the 2 minuses, look at the oxidation states. Oxygen is in group 6, so it forms 2 minus ions, oxidation state minus 2. And if I've got 3 of those, I've got oxidation state minus 6. Carbon's in plus 4, must be 2 minus left over. The carbonate ions are making the brown precipitate again, which is FeH2O3OH3, iron 3 hydroxide, same as before. It'll make some water, and it'll make some carbon dioxide as the bubbles of the gas. And then finally, my final one is concentrated hydrochloric acid. So concentrated hydrochloric acid can replace the water ligands to release 6H2O, but you can only get 4 Cls. They're quite large ligands, these, so you can't get more than 4 around. You can't get 6 as in water. You can only get 4 chloride ligands around a central metal ion, transition metal ion. I know it's -1 because I've got 4 Cl minuses. Cl is in group 7, so going to gain 1 electron and be Cl minus. So I've got oxidation state -1. I've got 4 -1s. I've got Fe3 plus, ion 3, and 3 plus and 4 minus leaves 1 minus left over, and it cancels. It works so it balances 1 minus on the right hand side with 3 plus and 4 1 minuses. A-level chemistry paper 1, specimen version 0.5. Let's have a look at this first of all. So before we start question number 1, let's have a look at different shapes of molecules. Let's go with no bonding pairs at all. Let's discuss no lone pairs at all bonding pairs. So 2 bonding pairs, no lone pairs, something like BeCl2. Beryllium's in group 2, 2 electrons in its outer shell. Cl's in group 7, wants to gain 1. So you have BeCl2. No lone pairs because beryllium's in group 2, 2 electrons in its outer shell. Both those are used in bonding pairs, and so it's a bond angle of 180. It's linear. Let's have a look at the next one where there's no lone pairs, but with 3 bonding pairs. 3 bonding pairs, something like BCl3 or BF3, where boron's in group 3, 3 electrons in outer shell, bonds 3 Fs, an F, an F, and an F, and so no lone pairs left over. All 3 electrons in the outer shell are involved in bonding pairs. Stays planar, so as long as these 2 numbers add up to 3 or less, it's going to stay planar. There are some slight exceptions to that rule that we'll see in a minute, but broadly, as long as these 2 numbers, the number of bonding pairs and the number of lone pairs, is 3 or less, then it stays planar. So it's trigonal planar, 3 in a flat shape, planar shape, bond angle 120. Let's have a look at the next one where there's bonding pairs and no lone pairs. So 4 bonding pairs, 4 add 0 is 4, so that's larger than 3, so it's no longer flat, it's no longer planar, and it can go into a tetrahedral shape to give a bond angle of 109.5. Remember that 109.5 because that's going to come in useful when we consider what happens when we introduce lone pairs. So let's have a look at 5 then. 5, so what actually happens is on 5, so 5 bonding pairs, so something like PCl5, this by the way was methane, something like that. PCl5, you get the trigonal planar shape, but you also get 1 up and 1 down, so the first 2 bonding pairs go as far away as they can do, and then the others go at 120 each. So you get a bond angle of 120, and then you get a bond angle of 90 to between the 2 bonding pairs that are up and down from the planar shape. 6 is octahedral, so 6 ends up with sort of square planar shape with an up and a down, so that's octahedral because it would have 8 faces if all of these were joined up. So that's octahedral, 6 bonding pairs, no lone pairs. Now let's have a look what happens. We'll ignore this one for a minute. Let's have a look what happens now if we end up with a 4 shape, a tetrahedral, but we introduce 1 lone pair. So 3 add 1 is 4, so it's not going to be flat. But what actually happens is one of those bonding pairs is replaced by a lone pair here. Now we need the 4 in to consider the shape, but we can't actually see a lone pair, so you just see the shapes of the atoms. So it's pyramidal. It's got 3, 1 in the middle, and then 3. So that could be something like ammonia. Nitrogen's in group 5, so 3 bonding pairs, and then the 4th and 5th electrons are as a lone pair. And if you remember, every time a tetrahedral shape, so 4 bonding pairs, one of the bonding pairs becomes a lone pair, you subtract 2.5, so 109 take away 2.5 is 107. And then the same thing works here for something like water, H2O, where you've got O in group 6, so 6 in its outer shell. 2 of them are involved in bonding pairs, and then there's 4 left over for 2 lone pairs. So if you take the tetrahedral shape and replace 2 of the bonding pairs with lone pairs, there, you actually only see the atoms. You don't see these these lone pairs here. You only see the atoms, and because there's 1, 2 bonding pairs replaced by 2 lone pairs, you subtract 109.5, take away 2.5, and take away 2.5 again for each of the lone pairs, and it comes out as 104.5, and that's V-shaped or bent. They've called it non-linear here, but V-shaped or bent is something easier to remember. And then there's other ones as well here, something like xenon tetrafluoride XeF4. Here we've got xenon with 8, so 4 bonding pairs, and then 4 electrons left over, so 2 lone pairs, and they do similar to an octahedral. These two repel the most, so lone pair repel the most, followed by lone pair bonding pair, followed by bonding pair in the electron pair repulsion theory. And so these two repel as far away as they can, up and down, and then they leave a square planar shape. So that's the only real example of where you end up with a planar shape. 4 add 2 is obviously larger than 3, so you would expect it not to be linear, but in this case it's linear because, you'd expect it not to be planar, but in this case it is planar because the 2 lone pairs push the 4 bonding pairs into a planar shape, bond angle 90. And then you can get other ones as well, so non-linear, so something with, say for example, 4 electrons in its outer shell bonding to 2 other atoms, then would end up with this kind of shape. And in that case you would have something like trigonal planar, but one of the bonding pairs is replaced by a lone pair, and so instead of 120 you subtract 2.5 and it comes out as 117.5, and that's called V-shaped again, or bent. Let's have a look at the actual question then now. Explain how the electron pair repulsion theory can be used to deduce the shape of the bond angle in PF3. So you've got 5 electrons, phosphorus is in group 5, so there's 5 electrons in the outer shell, 3 involved in bonding pairs, 5 take away the 3 that are involved in bonding pairs is 2, so there's a lone pair and 3 bonding pairs. So there's 1 lone pair and 3 bonding pairs. So we've got something like this. We've got pyramidal, so it's like a tetrahedral shape, but one of the bonding pairs is replaced by a lone pair, so you don't see that, so you only see the pyramidal shape. Tetrahedral, 109.5, take away 2.5 is 107. So 3 bonding pairs with 3 F atoms, 1 non-bonding pair or 1 lone pair. Electron pairs repel as far as possible. Lone pair repels more than bonding pairs. So you just got to name just got to quote the electron pair repulsion theory here, that electron pairs or lone pairs repel as far as possible, and then you can just say lone pair repels more than bonding pairs, or lone pair repels more than lone pair bonding pairs, and bonding pairs repel the least. So just give a little quotation of the electron pair repulsion theory, and then you can explain the shape and the bond angle. State the full electron configuration of a cobalt-2 ion. Well, cobalt's got an atomic number of 27, so it's got 27 electrons. 2 means cobalt-2 means the cobalt's in oxidation state, plus 2, it's lost 2 electrons, so it's got 25 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 3d7 adds up to 25. Suggest one reason why the electron pair repulsion theory cannot be used to predict the shape of the COCl4 ion. Well, you predict that it's actually tetrahedral because it's got a coordination number of 4. It's got 4 ligands, 4 Cls. So you actually predict it's tetrahedral. However, with transition metals, once you introduce electrons in a d orbital, there's too many electrons in a d orbital, so transition metals have got d orbitals, and yet there's too many electrons in the d orbital really for the electron pair repulsion theory to work. So all you need to say is too many electrons in the d orbital. That means the electron repulsion theory can't be used to predict the shape. Although, as I say, you'd probably predict it was tetrahedral. Predict the shape and the bond angle in the complex rhodium ReCl4. So if we're going to predict something, if we're forced into making a prediction, then Cl4 has got a coordination number of 4, and therefore you go with tetrahedral, bond angle 109.5. Question number 2. Explain why the atomic radii, so that's the radius, so the distance across an atom, so from the nucleus to the outer shell rather, decrease across period 3 from sodium to chlorine. So basically it's asking why the atoms get smaller. So as you go across a period, the number of protons increases, so the proton number will increase, the number of protons increases, so there's greater nuclear attraction between the nucleus and the electrons. So there's greater nuclear attraction, then the atoms essentially get smaller. Explain why the melting point of sulfur S8 is greater than that of phosphorus. Well, S8 is larger than P4, so if you consider something like oil, something like bitumen with very, very long chains compared to something like petrol with very, very short chains, then tar or bitumen has a higher boiling point than something like diesel or petrol that have got very short chains, and the same thing happens here. So S8 is bigger than P4, therefore you get a greater intermolecular attraction between the bigger molecules. You've got to name the force, it's van der Waals. So that's essentially the attraction between the nucleus in one atom in one molecule and the electrons in another molecule, and therefore you get more van der Waals forces, though. So therefore the melting point will be greater in sulfur because it's a bigger molecule. S8 is bigger than P4. Explain why sodium oxide forms an alkaline solution when it reacts with water. Tricky one there. An oxide ion is O2-, so the O2- is going to react with the water and it's going to make hydroxide ions. So alkalis or base are hydroxide ions. So you need to say that sodium oxide contains O2- ions, or the oxide ion reacts with water forming OH- or hydroxide ions. So oxide ions react with water to form OH- ions or hydroxide ions, and that's the actual equation if you actually want to know it. Write an ion equation for phosphorus 5 oxide with an excess of sodium hydroxide. Tricky one this. Phosphorus 5 oxide is P4O10. Hydroxide ions are OH-. You've got to know that you make a phosphite ion, PO43-, a phosphite ion. You just got to learn that, and you also make some water, and then you've got to balance it. Tricky one that, something to learn. Question 3. So this question is about fuel cells, and we've got electropotentials here. So these are all half equations. They're all reductions. So if you consider that the reduction oil rig, or oxidation is loss, reduction is gain, they're all gain in electrons. And the larger the value, the more likely it is to go ahead. So this one's very likely to go ahead to make F- ions. This one's unlikely to go ahead because it's the lowest value and it's minus. So something that's positive will go ahead, something that's less than 0, something that's negative won't go ahead. And when you combine two half equations, you have to reverse one round the other way because they can't both be reduction. You've got to have oxidation, reduction, you've got to have redox. So one's got to be oxidation, one's got to be reduction. When you reverse the equation the other way, then you add these two numbers together. So if, say for example, that one and that one we're considering, and this one went ahead and this one went back the other way, you'd minus that number and then add the two together to give a positive value overall for it to go ahead, for it to be feasible. So we've got each of these reactions happening in two cells joined by a salt bridge. Explain the function of the salt bridge. It allows ions to move between the salt bridge and complete the circuit. So ions in the salt bridge can move to complete the circuit. So it's allowing ions to move, electrical charges to move, to create a circuit between the two cells. Use data to choose the halide ion that is the weakest reducing agent. So a halide is something like F-, Cl-, Br-, I-. So if we have a look at these, we've got F-, Cl-, Br-, and I-. Even if you weren't sure, then you'd pick either that one, F-, or I-, the least one. So it's never going to be the two in the middle. It's never going to be Cl and Br. If it's the weakest reducing agent, it's at least one of those two. Now let's consider what weakest reducing agent is. So this one's really going to go ahead because it's got a large electropotential. So F- is really going to be made, plus 2.87. So F- really likes being reduced. It likes being reduced, gaining electrons to become F-. So it's unlikely to go the other way. It's not going to go the other way. Those halide ions are not going to be oxidized. So it wants to be reduced. It doesn't want to be oxidized. It doesn't want to lose electrons. So let's consider a reducing agent. Reducing agent reduces something else, causes something else to be reduced, and in the process it is oxidized. So your answer is F minus, because it really doesn't want to be oxidized. It doesn't want to reduce something else and become oxidized itself. So it doesn't want to become oxidized. It wants to be reduced. It wants to move to the right hand side. So your answer is F minus. Justify why sulfate ions should not be capable of oxidizing bromide ions from the data. Justify why sulfate ions should not be capable of oxidizing bromide ions. So let's have a look at sulfate ions. Sulfate ions are these, SO42 minus. So we've got plus 0.7. So if that goes ahead, it's plus 0.17. Bromide ions are here, Br minus. So if I reverse that, that becomes minus 1.07. So plus 0.17 minus 1.07, if the bromide ions are going in the opposite direction, gives a negative value. So sulfate ions is plus 0.17. Electropotential for bromide is minus 1.07. So the sulfate ion would be reversed, and it would give a plus value of 0.9. So that's actually what's going to happen. The sulfate ions would go this way to give minus 0.17, and the bromide ions would give plus 1.07. So that's the way that it would go, rather than the other way around. So sulfate ions should not be capable of producing of oxidizing bromide ions. That's true, because the sulfate ion has a lower electropotential than the bromide ion. So if either of them is going to be reversed, it's going to be the sulfate ion minus 0.17 to give an overall positive value of 0.9. So the electropotential for sulfate ions is less than that of Br, and because it's less than that, this would be the one that would be oxidized and go to the left hand side to give a minus 0.17 plus 1.07, therefore gives a positive value, a positive EMF overall. Calculate the value of the EMF of the hydrogen-oxygen fuel cell operating under alkaline conditions. So you need something with hydrogen and oxygen in the two equations, and alkaline conditions, alkaline is OH minus. So you're looking for something with hydrogen and oxygen in, and alkali is OH minus. So the two equations to use are these. Now, which one's going to be reversed? It's got to give a positive value overall. So if that stays positive and this one gets reversed to give a positive 0.83, this one is going to be reversed. So 4OH minus plus H2 is going to give 4H2O and 4E minus. So plus 0.4, and this one reversed plus 0.83, 1.23 volts. There are two ways to use hydrogen as fuel for cars. One way is a fuel cell to power an electric motor. The other way is as a fuel in an internal combustion engine. So it's just the major advantage of a fuel cell. It doesn't waste as much heat energy. Question 4 is about mean bond enthalpies. So I've got the bond enthalpies of each of the bonds in these reactants and products. So what I've got to do is I've got to calculate the strength of the bonds on the left hand side and calculate the strength of the bonds on the right hand side. These bonds here have been broken, so these are my reactants, and those bonds get broken. And in the products, the things that are made, bonds are formed, and you take this value, the value of all of the bonds broken, and you take away the value of the bonds being made, and that'll equal your enthalpy change. So it's the strength of all these bonds, take away the strength of these bonds on the right hand side, equals minus 49. So what I've actually got in there, so let's do spoilers. I've got CO2, I've got 2 lots of CO, I've got 3 lots of H2H, and I haven't got that value, that's what I'm trying to find out. So my bonds broken are 2 lots of 743 plus 3 lots of HH, I don't know that, and the bonds formed, and here I've got CH3, so I've got 3 C2H's, so I've got 3 412s. I've got a carbon to oxygen, so I've got a 360, and I've got an O to an H, so I've got a 463, and in H2O I've got HOH, so I've got 2 OH's, so I've got 2 463. So minus 49 is 2 times 743, add the 3 H to H bonds that I don't know, take away, so I'm taking away, subtracting the values of the bonds that are formed. So bonds broken take away bonds formed. So I've got 3 times 412 are my CHs, C2Hs. I've got carbon to oxygen, which is a 360. And then I've got an O to an H, and I've got 2 more O2Hs here. I've got 3 times 4, 6, 3. And if I resolve all that, minus 49 is 1486. Add 3 lots of the H2H bonds, which I don't know, take away 285. Take the minus 2985. Take the minus 2985 across the other side, it becomes a plus. 1486 plus becomes a minus, and that equals 1450 is the value of 3 H2H bonds. So 1 H2H bond is 1450 divided by 3, 483. Suggests one reason why the data book value for the HH bond is different from that, because these are real values, they're not mean bond enthalpy values. So the true values are not actually mean bond enthalpy values. So the mean bond enthalpy values are not the same as the actual or true values of the enthalpies of the actual chemicals. The bond enthalpies in a real reaction actually change from the average bond enthalpy. This is just an average bond enthalpy over a number of different reactions. It's just one environmental advantage of manufacturing methanol fueled by this reaction, using up carbon dioxide. Use Le Chatelier's principle to justify whether the reaction is carried out at high pressure rather than atmospheric pressure. Let's have a look. So I've got 1 mole of carbon dioxide and 3 moles of hydrogen. I've got 4 moles of gas on the left hand side. I've got 1 methanol gas and 1 water gas. I've only got 2 moles of gas on the right hand side. So I've got 4 moles of gas on the left, 2 moles of gas on the right hand side. So if I increase the pressure by Le Chatelier's principle, increasing pressure, Le Chatelier's principle will try and lower the pressure. It lowers the pressure by turning a large volume down in a small volume. It'll shift the position of equilibrium to the right hand side to lower this pressure by Le Chatelier's principle and increase the yield of methanol in the process. Suggests why a catalyst used in the process may become less efficient if carbon dioxide contains impurities. Well, a catalyst has got active sites just like an enzyme. So it locks in the molecules and brings them close together. So impurities will block these active sites. In a laboratory experiment to investigate, we've got an equilibrium reaction here, and we've got some values of some of the chemicals before the reaction started. Then at equilibrium, we will need to work out the values of each of them at equilibrium and work out an equilibrium constant. There's Kp here, which means it's they're all gases, so it's not got concentration, it's actually the pressure of each of these. If you've got gases, then pressure is the same as concentration, so you can place concentration with pressure if you've got all gases in a reaction. So let's do spoilers first of all, so you can see how I'm going to set this out. So carbon dioxide and 3 moles of hydrogen, making 1 mole of methanol gas and 1 mole of steam or water. Initial number of moles, 1 mole of carbon dioxide, 3 moles of hydrogen. It doesn't mention anything about the methanol and the water, so we haven't got any of those. And at equilibrium, it says at equilibrium the yield of methanol was 0.86, so I've got this value here. Now when 1 mole of methanol's made, 1 mole of water's made, 1 and 1. So one of these and one of these are made at the same time. So this must be 0.86 as well. So they're made in equal amounts. 1 mole of carbon dioxide makes 1 mole of methanol, so if I'm making 0.86 moles of methanol, then 0.86 moles of this must be used up because it's a reactant. 1 mole of carbon dioxide reacts with 3 moles of hydrogen, so 3 times 0.86 or 2.58 must be used up. Let's have a look what I've got in the equilibrium mixture. I started with 1, I've used up 0.86, I've got 0.14 left. I started off with 3 moles of hydrogen. I've used up 2.58, 3 take away 2.58 is 0.42, and I've got 0.86 of this made and 0.86 moles of water made as well. So what I actually do is, for pressures, for concentrations, then I take the amount and I divide by the volume. So the total volume is 2.28. When I add up all of the volumes of each of these, or numbers of moles of each of these, that equates to volume as well. So number of moles can equate to the volume. So total moles of gas 0.14, 0.42, 0.86, 0.86, 2.28 moles of gas. And what I therefore do is I work out the fraction of carbon dioxide that I've got. So I've got 0.14 moles of carbon dioxide. So I divide therefore, so the fraction of carbon dioxide in the mixture, I've got 0.14 moles out of a total of 2.28 moles, 0.061. So I work out the fraction of carbon dioxide in the mixture. Hydrogen 0.42 divided by the total number of moles 2.28 is 0.184, so that's the fraction of hydrogen that I've got in the mixture, and I work out the fraction of methanol and the fraction of water as well, 0.377. So now I've got the fractions of each of these contributing to the total pressure. So 500 kilopascals is the total pressure, and the fraction of carbon dioxide that I've got in the mixture is 0.061. So I'll multiply the fraction by 500 and I find out the pressures that each of these are contributing. So the number of moles, or the fraction of the number of moles, then gives a fraction of the pressure. So these are the pressures that I've now got. So I multiply the fraction of number of moles by the total pressure, and I work out the fraction of the pressure that's been provided by each of these. These last two are calculated by multiplying 0.377 by 500 to give 188.6, and if you add up all of those it should equal 500. Now an equilibrium constant is would be the concentration of methanol multiplied by the concentration of water divided by the concentration of carbon dioxide divided by the concentration of hydrogen to the power 3. It's the same for pressures, so I'm just replacing concentration with pressures, and I put these values in now. Each of these pressures, called partial pressures, I put those in and work out a value is 0.00151. So that's my equilibrium constant, or my Kp, 0.0051. And then I do the same things again. I've got pressure times pressure divided by pressure times pressure to the power of 3. So I've got kilopascal twice on the top, and kilopascal multiplied by kilopascal, kilopascal per kilopascal. So I've got 4 kilopascals on the bottom. So 2 kilopascals cancel. I end up with 2 kilopascals on the bottom. And that's kilopascal to the -2 if I take it to the top. Question 5 is about entropy. So entropy, so delta S, or entropy, is the entropy of the products, the things on the right hand side. Take away the entropy of the products of the reactants on the left hand side. So you need to work out the entropy of the right hand side, which is, the entropy is 238, add water 189, and then take away the entropy of the reactants, which is 214, and I've got 3 moles of H2, so it's 3 lots of 131, so it's 427, take away 607, minus 180, and then it's in the units of entropy here, joules per Kelvin per mole. Okay, so that's my entropy there. Now then, it then needs you to work out delta G. So that's what it's actually asking for you. So it's asking for the Gibbs free energy change, delta G, which is delta H minus T delta S. So I've got delta H here, but that's in kilojoules per mole, and my units of entropy in joules per mole. So I'm going to get my joules per Kelvin per mole into kilojoules. So joules into kilojoules, if I'm taking joules into kilojoules, I divide by 1000. So now if I divide my 180 by 1000, it's minus 0.180 kilojoules per Kelvin per mole, because then that's going to match with my kilojoules for my delta H. So now delta G is delta H, which is minus 49. Take away the temperature, which is 250, but that needs converting into Kelvin, because if you look here, I've got units in Kelvin. So to convert 250 degrees C into Kelvin, add on 273, it's 523 Kelvin. So my T delta S, so is 253 multiplied by delta S, which is minus 0.180. So let's do a quick recap. So my delta G is delta H, which is minus 49. Take away temperature in Kelvin, 523, multiplied by delta S, and I've got it in kilojoules per Kelvin per mole to match the kilojoules of the delta H. And that is minus 49, take away minus 94.14. A minus and minus is a plus, so minus 49, add 94.14, it's 45.1 kilojoules per mole. How do I know that it's kilojoules per mole? Well, delta H is in kilojoules per mole, delta S is in joules per Kelvin per mole per Kelvin, Kelvin to the minus 1, so Kelvin's on the bottom, and I've just multiplied by a Kelvin. So I've got temperature is a Kelvin multiplied by delta S, which is joules, divided by Kelvin divided by mole, so the two Kelvins cancel, so that becomes kilojoules per mole, so my answer is in kilojoules per mole. Calculate a value for the temperature when the reaction becomes feasible. Well, feasible when delta G is 0. So delta G is delta H minus T delta S, so 0. So 0 delta G is when it's feasible, equals delta H minus T delta S. I'll take minus T delta S across the other side so it becomes positive, so T delta S equals delta H. So if delta H equals T delta S, then I've got to work out the temperature, so I'm trying to get temperature on its own, so I divide by both sides by delta S, so T equals, so take delta S onto the bottom, onto the other side, or divide both sides by delta S. T is delta H divided by delta S. So delta H is minus 49, delta S is minus 0.180, so my temperature is minus 49 divided by minus 0.180 is 272, and it's in Kelvin. Gaseous methanol from this reaction is liquefied. Draw a diagram to show 2 moles of methanol. So methanol is meth, CH3OH, CH3OH, and so I've drawn 2 CH3OH. Now my oxygen has got 2 bonding pairs, the H and the CH3, and it's got 2 lone pairs because oxygen's in group 6, so one in each bonding pairs. Leaves 4 electrons left over, 2 lone pairs. Now I've drawn 2 molecules, and I've drawn the bonding pairs as these sort of lobe shape, but you could just put a pair of electrons there and a pair of electrons here. You've got to draw the pair of electrons in because it's the pair of electrons here that attract with a hydrogen bond to the delta plus on the H. So remember, you've got a hydrogen bond here, you've got a hydrogen bond into an oxygen. Anytime you have a hydrogen bond to an oxygen or a nitrogen or a fluorine, then the oxygen is very much more electronegative than the hydrogen, and so the hydrogen ends up with a delta plus, and the O, or rather the lone pair of electrons on the O, attract the delta plus, and you line it up like this. The lone pairs of electrons on the oxygen attract the hydrogen, and the lone pairs of electrons on the other oxygen are pushed the other way. So there's a dotted line to show an intermolecular hydrogen bond between the lone pair of electrons on the oxygen and a hydrogen of another molecule, and you line them up in this way with the hydrogen in the middle. So oxygen, hydrogen, oxygen, because the lone pairs of electrons on the oxygen repel the lone pairs of electrons on the other oxygen as far as they can go in a linear sort of fashion. Explain why methanol is so easy to liquefy, because it's got hydrogen bonds. So it's got hydrogen bonds which are strong intermolecular bonds, so it's more likely to be a liquid than a gas. Question 6. Ammonium chloride, when dissolved in water, can act as a weak acid. You've got a graph, you're adding sodium hydroxide, so you've got ammonium chloride, which is NH4+, dissolved in water. This is acting as a weak acid, and I'm adding some sodium hydroxide, which is a strong base, to the solution. The pH is changing, and I'm measuring the pH, so I'm adding a little bit of sodium hydroxide as I go, and I'm measuring the pH every time 1 centimetre cubed of sodium hydroxide has been added. I'm getting a new point and I've drawn a curve. Explain what piece of apparatus could be used to measure different volumes. Well, it's going to be a burette. More suitable than a pipette. Well, it can deliver different volumes, so I can add 1 and then 2 and then 3 and then 4. So a burette, because it can deliver different volumes as I go along. I can keep adding 1 centimetre cubed at a time and keep measuring the new pH. Use the information with the curve to explain why the end point of the reaction would be difficult to judge because there's no sharp increase in pH. There's never a point where I get an equivalence point, an end point or an equivalence point where there's a sharp change in pH and where an indicator would change colour. So no sharp change in pH, no end point, no equivalence point. An indicator would not change colour. The pH at the end point or equivalence point of this reaction is 11.8. Use this value Kw. If I'm given a Kw equals the H plus concentration multiplied by the OH minus concentration. That's what Kw equals. So 1 times 10 to the minus 14 is H plus concentration multiplied by OH minus concentration. Use the pH value is 11.8. So first of all, let's go back a stage. pH is 11.8. pH equals minus log to the base 10 of hydrogen ions. So 11.8 equals minus log to the base 10 of hydrogen ion concentration. So what you do is reverse the reverse sign, get rid of the minus log by making it both sides, change the sign on both sides. So instead of minus log H plus concentration equals 11.8, you say log H plus concentration equals minus 11.8. Then you can inverse log or shift log or second function log, whichever one your calculator does. Remove the log, and H plus concentration is 1.58 times 10 to the minus 12. That's the only thing you can do with pH, is work out pH equals minus log to the H plus concentration. That's what it's taking you down the path of working out H plus concentration. Now we know Kw equals H plus concentration multiplied by OH minus concentration. So 1 times 10 to the minus 14 equals the H plus concentration, which we've now got multiplied by the OH minus concentration. OH minus concentration 1 times 10 to the minus 14 divided by 1.58 times 10 to the minus 2. OH minus concentration is 6.33 times 10 to the minus 3. The expression for the acid dissociation constant of ammonium ions is this. Okay, the initial concentration of the ammonium chloride was 2 mole per decimeter cubed. Ammonium chloride solution, remember back here, it says ammonium chloride is this, NH4 plus, when it's in water. So the ammonium chloride solution 2 mole per decimeter cubed is this. So Ka equals NH3 multiplied by H plus concentration divided by 2, because that's the concentration. 2 is NH4 plus, and I've been given Ka, and I've got this equation here. So I've got Ka equals, oh sorry, I'm trying to find Ka. Ka equals this concentration multiplied by this concentration divided by 2. So since NH3 is made at the same time as H plus, you could replace NH3 with H plus and say Ka equals H plus times H plus divided by 2. So Ka equals H plus squared divided by 2. And then we're short of a number. We haven't got a number. So we need a number. So if I need a number from this, I've got to read from the graph, because I've not got Ka and I've not got H plus concentration. So I need one of them. So if I read from the graph before any sodium hydroxide has been added, here my pH is 4.6. So 4.6 is when no sodium hydroxide has been added at all. So I've got a pH of 4.6. Now what's the only thing I can do with a pH of 4.6? 4.6 is minus log to the base 10 of hydrogen ion concentration. So I reverse the sign on both sides. So minus 4.6 is plus log H plus concentration, inverse log, shift log, second function log of minus 4.6 will give me the H plus concentration. And so now I've got H plus concentration squared, so I square this, divided by the 2 mole per decimeter cubed, which is the concentration of NH4 plus ammonium chloride. 3.15 is Ka, and that's what I'm trying to find. So I worked out that I must be reading from the graph to find the H plus concentration in this reaction here before any sodium hydroxide had been added. The solution contains equal concentrations of ammonia and ammonium ions. Well, ammonia is NH3 and ammonium is this, so if that value NH3 equals NH4 plus, so a value on the top equals a value on the bottom, because ammonia and ammonium ions, it says, are of equal concentration, then those two will cancel and Ka will equal H plus. So if Ka equals H plus, K equals H plus, 3.15 times 10 to the minus 10 equals H plus. That was the value that I got of Ka, and so now it wants me to work out the pH. pH is minus log to the base 10 of hydrogen ion concentration minus log to the base 10 of 3.15 times 10 to the minus 10 is 9.5, which is correct because it says it's an alkaline or a basic solution, so that's going to be above 7. And ammonia is a weak alkali or a weak base, so that seems to be about right. Question 7, so we've got some ionization energy data. So first of all, why do the ionization energies, the successive ionization energies increase? Well, the number of protons aren't changing. Every time you remove an electron from the first, second, third, fourth, fifth and sixth ionization energy, the nuclear attraction, the attraction from the protons in the nucleus isn't changing, but the number of electrons are decreasing. So there's the same nuclear attraction for an ever-reducing number of electrons. Therefore, proportionately, the attraction increases, and so it becomes harder and harder and harder, or it requires more and more energy to remove successive electrons. However, the question is asking, 7.1 is asking, which element is calcium? Well, calcium's in group 2, so removing the first 2 electrons gets increasingly difficult, but removal of the third electron from an energy level underneath, which is full and stable, is going to be very difficult. So there's a jump then between the second and the third, and the jump then I can see is Y. 1150 to 4940 is the large jump. That means that calcium in group 2 with 2 electrons in the outer shell, the third electron is particularly difficult to remove because it's coming from a full stable energy level underneath. Bit trickier this one, vanadium, because you've got to work out that it's 4s2,3d3. So 4s2,3d3 has got 5 electrons in its outer 5 outer electrons. 4s2 will be removed first, and then the 3d3 will be removed, and then you're removing from a full 3d2 orbital underneath. So the first 5 electrons are increasingly difficult to remove, but the 6th electron coming from a 3d2, a full suborbital underneath, is going to be difficult to remove. Between the 5th and the 6th, 6280 to 12400 is a large jump. So the answer then is X. Why was it vanadium? So it's just asked me to explain that there's a jump in ionization energy between the removal of the 5th and the 6th electron. So vanadium, which has got 4s2,3d3, 5 outer electrons, it's likely to be vanadium. An acidified solution of NH4VO3 reacts with zinc. Explain how this reaction shows that vanadium is in at least 2 different oxidation states. The easiest way to note that it's in different oxidation states is when it changed its oxidation state as a transition metal, it changed its colour. So 2 different colours are probably observed, and each colour is due to the vanadium being in a different oxidation state. I think this is one of the hardest questions, or if not the hardest question on the paper. The vanadium has vanadium in 50 centimeters cubed of 0.8 mole decimeter cubed solution. So first of all, I've got a volume and a concentration, so I've got to get that into decimeter cubed, and then I can use concentration as moles divided by volume in decimeter cubed. Centimeter cubed up into a larger unit like decimeter cubed, I divide by 1000, so that's 0.05. So concentration 0.8 equals number of moles divided by 0.05. So my number of moles is 0.8. My concentration multiplied by 0.05, which is 0.04. I'll leave this up as spoilers then for SO2. Slightly more difficult, well, quite a lot more difficult really, because we've got PV equals nRT. We've obviously got PV equals nRT because I've got a volume, but I've got a temperature, I've got a pressure, and I've got a gas constant R. So I've got PV equals nRT, so it's relying on me knowing the second equation. And what's also tricky is that these aren't in the right units either. 506 centimeter cubed for PV equals nRT. The volume's got to be in meters cubed. So centimeters cubed up into decimeter cubed, you divide by 1000. 506 divided by 1000 is 0.506. And then to get up into decimeter cubed, up into a larger unit still, to get up into meter cubed, it's divided by 1000 again. So it's 0.00506 meters cubed. If that weren't tricky enough, then you've got degrees Celsius, and that needs to go into Kelvin. So you've got to add on, therefore, to get into Kelvin, then you've got to take your temperature, 220, and add on 273 to equal 298. So now we've got the temperature in Kelvin. Now we've got 98 kilopascals, and that's not correct either. You've got to get that into pascals. And so a large unit down to a smaller unit, you multiply by 1000. So that's 98 multiplied by 1000 is 98,000 pascals. PV equals nRT. We can start putting these in now. P is 98,000. Volume is 0.00506 equals N, the number of moles, multiplied by 8.31, which we're given is the gas constant, multiplied by the temperature in Kelvin 293, and I've got that there. I'd multiply these two out first, make it simpler. 49.588 equals N, the number of moles, and I'd multiply these two out, 2434.38, so N is 49.588 divided by 2434.83, 0.02. So this next stage is difficult now, even more difficult, because we've got to work out, we're working out that 0.04 moles of this reacts with 0.02 moles of this. So I've got 2 moles of the vanadium compound reacting with 1 mole of the sulfur dioxide gas. It's reacting in the ratio 2 to 1. So 2 moles of the vanadium compound react with 1 mole of SO2. So what's happened to SO2? Well, SO2 reacts to make sulfate ions, SO42-, and you can produce a half equation from that. How can I get that making that? Well, I've always got water and H plus that I can always add into a half equation, and electrons, of course, always needed in a half equation. Water and H plus to add in. So I'm going to need more oxygens on the left hand side because I've only got 2 O's and I've got 4 O's there. H2O, I'm going to need 2 H2O to make the O's balance, 4 on the left and 4 on the right. And now I've got 4 H's, I can make 4 H plus. So to balance a half equation involving H's and O's, I can always add water and H pluses. And now if I look on the right hand side, I've got 4 pluses, 2 minuses, I've got 2 electrons. Okay, so 2 moles, so I've got to get the 2 electrons. Where do they come from? They come from the other chemical that reacts, the NH4VO3, that's where the electrons come from. So 2 moles of NH4VO3 rather are not going to make 2 electrons, they're going to absorb 2 electrons, remove 2 electrons. So 1 mole of NHVO3 will remove 1 mole of these electrons. So the oxidation state is going to go down by -1. If it accepts an electron, its oxidation state is going to go down by -1. NH4VO3, its oxidation states of N are in -3, H is +1 and O is -2. Because N is in group 5, accepts 3 electrons, H is in group 1, loses 1 electrons, O is in group 6, gains 2 electrons. So now I can do some simple sums. -3, add 4 times 1, V, we don't know the oxidation state. O is 3 minus 2's, and that's all got to equal 0 because there's no charge on this, and so my oxidation state of my vanadium must be plus 5 to make all of those numbers equal 0. If it's going down by minus 1, because it's accepting an electron, so it's accepting a minus and going down by minus 1, its new oxidation state must be 4. Question 8. 8.1. A coordinate bond is formed when a transition metal ion reacts with a ligand. Explain how this coordinate bond is formed. Well, first of all, a coordinate bond is just a covalent bond, that's all it is. The only difference is, instead of having a pair of atoms each putting one electron in each, then one of the atoms has put both of the electrons into the pair, and that's the ligand coming in. So the ligand has donated a pair of electrons to form a covalent bond, and that happens to be called a coordinate bond. So it donates a pair of electrons to the central metal ion. Describe what you observe when dilute aqueous ammonia is added dropwise and then to excess to a solution containing copper 2 ions. Well, first of all, you get a light blue precipitate, and then it's going to redissolve and form a deep blue solution. So what actually happens, let's do spoilers, you get a light blue precipitate and then it dissolves to give a dark blue solution, and copper has got 6 ligands around it, and it's copper 2, it tells you it's copper 2 in the question, and water has no charge, so 6 waters. Cu, if that's in 2 plus oxidation state, must be 2 left over, and what actually happens is that the ammonia replaces 2 of the waters. 2 of the waters get replaced and they form OH2, and it doesn't have any charge, and that's why it's a blue precipitate. Not having any charge means that it's not going to dissolve in the water. It's got no charges to dissolve to form any polar bonds to the water molecules. So having no charge means that it's a blue precipitate. So 2 of the waters have become OH2 with no charge, and they become OH2s, and therefore the 2 H's from the H2O, so as H2O has formed OH twice, then the 2 H pluses have reacted to form 2 NH4 plus, and the charge is balanced. Then what happens is that this reacts with more ammonia, and 4 of the ammonias react and form 4 ammonia ligands, 4 amine ligands, NH3, 4 of them, and that replaces both the OHs and 2 of the waters. Ammonia has no charge, water has no charge, and therefore it's got its 2 plus charge left over. The OHs form OH minuses, and you get 2 waters. When the complex ion CuNH3,4H2O2 reacts with 1,2-diaminoethane, so the ammonia molecules but not the water molecules are replaced. So these ammonia molecules are replaced by 1,2-diaminoethane. Diamino means that it's got 2 NH2 groups, and having 2 NH2 groups, it's a bidentate ligand. It means that it forms 2 coordinate bonds. So instead of needing 4 of these ammonias each, which make a single coordinate bond, we only need 2 diaminoethanes, because each of those forms 2 of these bonds, and we need 4 bonds in total, therefore we only need 2 of these. So the equation is, you take this complex ion here, you have diaminoethane, ethane 2 carbons, diamino, there's an NH2 on each of the 2 carbons, and then that forms 2 ligands, H2O2 plus. This diaminoethane has no charge, and therefore this can have 2 plus overall, because the copper 2 is maintained in its 2 plus oxidation state, and the 4 NH3s come off, so the 4 amino ligands form 4 ammonia molecules, and it tells you that in the question. Suggest why the enthalpy change for the reaction in question 8.3 is approximately 0. Well, you've got a coordinate bond here from an N to a Cu, and you've got another coordinate bond here from an N to a Cu, so the energy in breaking those bonds and then reforming those bonds must be fairly similar. You've got the same kind of bond being broken, the same kind of bond being formed between an N and a Cu, and between an N and a Cu, because it's the N that donates the pair of electrons to form the coordinate bond. And you've got the same number of coordinate bonds here. So this forms 4 coordinate bonds, this forms 4 coordinate bonds, because each of these 2 diamino ethane molecules, being a bidentate ligand, form 2 coordinate bonds. So the Cu-N bonds have similar energy, so the ones broken here have similar energy to the ones formed, and the same number of bonds are broken as made, i.e. 4. Explain why the reaction 8.3 occurs despite having an enthalpy change that is approximately 0. So if your enthalpy change is 0, there must be something else coming into play, and that's entropy. So entropy is the measure of how much chaos is going on, really. So how chaotic, or the number of molecules. So we've got 3 molecules forming 1, 2, 3, 4, 5. So it's becoming more chaotic. So entropy is increasing. Now if entropy increases, delta G, free energy change, must be negative, because delta G equals delta H minus T delta S, minus T delta S being the entropy. So delta S is the entropy, and if it's minus T delta S, that becomes a larger minus value, and therefore Gibbs free energy change delta G becomes negative.